for the introduction, Professor Ferruti. It's a pleasure to participate in this meeting. I want to really thank the whole organizing committee for inviting me to take part of this, and also to the whole technical team, because I know that the virtual conference is really a big challenge. So I really thanks everybody for making this huge effort. Well, in my talk, what I'm gonna show you today is summarizing a project in which we have been working for the last decade. It's a very easy project. Basically, I will try to show you how you can make adhesive polymer using click chemistry. Okay, this is gonna be the topic of my talk. So this is the outline of my talk. Basically, I will make a brief introduction on the concept of click chemistry. I know that in a polymer audience, this may not be necessary, but it could be possible that there is some people that has never used it experimentally, click polymerization. So I will just mention the key concept that I would like you keep in mind in order to understand how you can make these adhesive polymers. Yeah, then after that, I will just also mention briefly a few properties that we can use in order to make other application, like for example, conductive metal adhesive, metal glass adhesion, and also how we can go with anti-corrosion coatings. So first of all, if we want to put in context the concept of click chemistry, we should mention first the work of Professor Sir John Comfort. This is a very famous Australian-British chemist, well known by his work on the stereochemistry of enzymatic reaction. As you know, he won the Nobel Prize in 1975, shared with Vladimir Prelog. And this is interesting because he always say that the ideal chemical process is the one that can be carried out in a bathtub, as you see here, by one-arm operator who cannot read, with the product being collected from the drain hole in 100% yield and purity. Yeah, so I found that really interesting. Of course, we all want a process like this. This was also an inspiration for Professor Sharpless. As you know, Professor Sharpless in 2001 was the one that introduced the concept of click chemistry. Basically, he did it to identify a number of robust, efficient, and orthogonal reactions that can emulate the modular approach that nature used to make a molecule. So if you think about what are the click reactions, usually this summarizes pretty much what are the common characteristics of the click reaction, right? So basically we have reaction where we involve carbon heteroatoms bond formation, starting from high energy building block. These reactions are pretty selective with a broad scope, and also the functional group compatibility is pretty high. The reactions are usually or must be simple to carry out in a few steps with high yield, maximum convergence, and also many of the assembly reactions that we know are within this type of chemistry, right? So of course there is a number of electrophile and nucleophile, as you can see here, that we can combine in order to develop processes that meet the requirement of a click reaction. And everybody knows this. But of course, if we have to think about a prototype of a click reaction, this is without any doubt the cycloaddition reaction between Si and alkyne, right? So if you think about how this reaction has been developed, there is a few things interesting that has a lot to do with the adhesive polymers. First of all, when you heat it up, a mix of acid and alkyne, as you know, you get almost an equivalent mixture of the two isomer triazole, yeah, the 1,4 disubstituted and the 1,5 disubstituted triazole. The contribution of Professor Sharpless and co-worker was to find out that if you add copper-1 ions, then not only accelerate the reaction, but it also provide only one isomer, so the 1,4 disubstituted triazole. Also, this catalysis by copper was also reported in solid phase by Professor Meldal, almost at the same time like Professor Sharpless in solution. So we are not going to discuss the mechanism of the reaction, but I want that you keep an eye on one of the intermediate, which is the key intermediate of this reaction. This is this copper acetylide intermediate. This is really critical for making the metal adhesive that I will show you in a moment. This reaction is, as you know, it works in very mild condition in a wide range of pH. It can work in water, in organic solvent, in solid phase. It is not really sensitive to the nature of the alkyne and acid, which is pretty good. It's stereoselective. Yeah, if we use copper-1 in situ. So if we use copper-1 directly, or if we use copper-1 making the reduction of copper-2 in situ. The reaction is also, so the catalysis can be enhanced by the use of some ligands. And as you know, also the triazole are pretty interesting motif because we have property like pi stacking, hydrogen bonding acceptor. We have an important dipolar moment. And overall, these are an orthogonal reaction, so the acid and alkyne will react to each other without affecting other functional groups. It is a irreversible process, but most importantly, from my point of view, is that alkyne and acid can be easily introduced into most of organic compound, right? And if you are an organic synthetic chemist, you will appreciate this a lot, because if that would not be the case, then probably the development of the click chemistry will be totally different. Yeah. So the fact that we can easily put alkyne and acid in most of organic molecule has pushed this chemistry to many applications. Okay, so now I want to show you how we came. So what I said before was that you keep in mind the key intermediate of the click reaction, which is the copper acetylide. And now I want to show you how we came up with the idea of making adhesive. And for this, you need to look at the literature first. You will see that there is, from a long time ago, the 1,2,4 triazoles, not the 1,2,3, but the 1,2,4 triazole has been used as a corrosion inhibitor for copper surfaces. This is well known, and we understood that 1,2,3 triazoles should provide probably the same or very similar affinity by metal surfaces, right? There is not much different in terms of the interaction. That was the first thing we considered. Of course, the 1,2,3 triazole has not been used in so much as the 1,2,4 triazole for corrosion. But the answer for this, or the reason for this, probably is because before the click chemistry, it was not so easy to fabricate a 1,2,3 triazole. But now with the click chemistry, we have access to almost any triazole we want to make, right? And the other thing which is very important is what you see here. This is the cycloaddition reaction. We need very small amount of copper-1 ion as a catalyst. So in solution, for example, you need between 200 and 700 micromolar to catalyze this reaction and increase the rate up to 10 to the power of 7. This is important because we don't need too much copper-1 ion to move this reaction. And there is one thing which is also critical for this project. And this is something which is very elemental, this comproportionation equilibrium when you have copper 0, and copper 2. When you have these two copper, then you will generate spontaneously, of course, copper-1 ion, right? And this is important. I will show you how we can use this to create these two ideas you see here, this precedent with the 1,2,4 triazole, and this formation of copper 1 ion from this comproportionation equilibrium to make adhesive polymer. Before that, I also want to tell you that the adhesive market is also a huge market. So from the economical point of view, looks like an interesting project to get involved, right? There is the global consumption of adhesive is quite big. So say this, sorry, I want to reduce the volume here. So how we can make the adhesive? We can do it in a similar way that nature does very strong adhesive as well. If you think about the muscle, right? So you know that they can stick to many surfaces very strongly and support very harsh conditions. Very briefly, if you know the mechanism of this adhesion, basically the muscle expel some proteins which are rich in this DOPA unit, right? This dihydroxybenzene unit. And what happens is that when the water, when the muscle get in contact with the water, the pH is a little bit alkaline, and that is the driving force for expelling these proteins, right? Rich in DOPA. And then when the muscle stick to the surface, to a rock, they recognize the presence of different metal ions like iron 3, for example, and they form this kind of cross-link or this coordination complex, making a very cross-link structure. And this is the main driving for the adhesion of these animals. So if you think about this, is really cool because they are using their own substrate to promote a reaction, in this case this cross-link, to make an attachment to the substrate. Yeah, so basically the substrate induce the formation of the cross-linking. So if we think about this, we can do a very similar thing with the click chemistry. So we can take a surface where we have a copper 0, and of course we will have automatically copper 2 as well, a copper 2 oxide layer. And therefore, on the surface of a copper, we will have enough copper 1 ions that should be possible to use to promote a click reaction. But the first thing we have to demonstrate is that we can indeed make a polymer, and this is one of the first polymer we make, and indeed is one, if not the first polymer that was made with the click polymerization. This is a very simple monomers, divalent Si and divalent alkyne. And then you can see you can really easily fabricate a large polymer in solution, right? But now, how to make it the adhesive? Then what I was saying is you take a surface, a copper plate, and you put a little bit, a mix of 2 polyvalent alkyne and Si, and you put it directly on the surface of a metal, right? This is a plate like this one you see here. You put the mix of the alkyne and the Si, and then you just cross the plate. What happens is that the copper 1 ion generated on the surface of the copper will catalyze the reaction, make a polytriazole, and the 1,2,3 triazole will stick to the copper. Yeah, we know that by click chemistry because we know that the triazole has a lot of affinity by copper. Indeed, we have always to remove the copper when we make a click reaction. And taking advantage of that affinity, once the polymer is growing between the plate, then they stick to the surface, right? And this is how we make the adhesive. Pretty easy. You can see that with only 50 milligrams of this monomer, we can, and that was the first experiments we made. We can hold more than 40 kilo of weight. And now we have much better formulation that support much higher loading. And here you can think that this is limited to copper surfaces, but that's not true, because what happened is that this is limited to the presence of copper 1 ion. So if in our formulation we put a little bit of copper 1 ions to promote the polymerization, then we can also glue other metal surfaces like zinc, aluminum, brass, and so on. So it's no limit to the nature of the surface, but it's a limit to the presence of the copper 1 ion, right? And of course, there is a number of variables that I don't have time to discuss, but the number of variables that are important that will influence the strength of that adhesive, right? Like, for example, the number of arms that we have in the monomers, the pressure, the temperature, the time, and so on. Now, if we look at what happened really in between the plate, this cartoon shows you a little bit what is the main step of this. First of all, the metal surface serves for two roles. The first is to provide copper 1 ions, from the surfaces. Very close to the surface, it's likely that the concentration of the copper 1 ion is higher. And then they also stabilize these ions. So the other role that this copper surface has is the formation of to promote the formation of the copper acetylide. And remember that the copper acetylide is the key intermediate for the click reaction, right? So basically what happens is that you promote the binding of the growing polymer to the metal surface. And we also have here a potential interaction between the triazole that we are forming and the metal surface. Yeah? So here we involve sigma bond complex or nitrogen sigma bond donor interaction. And something very important is also that once we are attaching this growing polymer, then in the inner part, we also have a cross-linking process, right? And this is important to realize that the copper triazole interaction, these are labile interaction. Yeah, this copper can move, and this is very similar to what happened in a radical polymerization, right? And because they can move, they create this kind of hot spot of catalytic reactivity. And this is one of the reasons why this reaction works so well on metal surfaces. And as you can see here, we can also etch a little bit of the surface by coordinating the polymer on the surface. Of course, if you also have in your monomer or you add a ligand that can stabilize the copper 1 ion, then you also facilitate this click polymerization. And this is something that you can play as a variable as well. In this slide, you can see a huge variety of monomer. This is just to show you that it is pretty easy to synthesize all this monomer. We have much larger library of compound. But what I want to show you is that, for example, mix like these two monomer provide much higher strength than commercially available adhesive used for the same purpose, like this Bell adhesive. So depending on the application you want, you may play with the different monomers. Now, this polymer in general are not very the original polymer that I show you are not really good because they are brittle in nature. So if you look at the thermal property of this polymer, they are really brittle. And one way to improve the performance of this adhesive is by incorporating some flexibility to the network. So how can you do that? You fabricate alkyne acids that you add in a very tiny amount to the formulation. So you have the formulation, the main formulation, which are, for example, these two molecules, and then you add a little bit of this flexible cross-linker, right? And if you do that, here I will not go into the whole table, but you can keep an eye on, for example, this one here and this one here. And these two we mix in a 4% respect to the total SI and alkyne. We mix with let me go back, with this one here. So this is our adhesive, and these are our additive, right? So when we put 4% of this one, then you can see that we can increase more than double the strength of the adhesive, right? So it's very easy to modulate the flexibility of this adhesive. We look at force displacement curve to study also different parameters. And here, what is important to realize is that you have to balance a little bit between the speed of the reaction and the cross-linking degree of your polymer, right? So because, for example, as you can see here, we can increase the temperature to decrease the curing time of the adhesive. So if we increase the temperature, then the polymerization is faster, then the time for getting the final adhesion is lower. But if we increase too much, then we also dilute the effect of the cross-linking of the triazole, sorry, and then it's bad. So we found that 70-degree maximum is the optimal temperature to cure this adhesive, but we can also do room temperature if we need it, but we need longer time. Same thing happened with the ligand. If you use a ligand to accelerate the reaction, then a little bit of ligand is good. So 50 millimolar concentration of a ligand is good to stabilize the copper 1. But if we put too much ligand, then we also get into a decrease of the adhesive strength. And same thing happened with the environment. So we have an oxidation process here from copper 0 to copper 1. If we put just pure oxygen, then we don't have adhesion. The optimal case is just the air, which contains 20% of oxygen. And this is basically we can also, in air, we can also decrease the speed by increasing a little bit the temperature, but again, not too much, because then we go in the other way around. Another thing we can do as well with this adhesive is to make it conductive. This is very important and interesting for electronic industry. These polymers that I show you are not conductive in nature, but if you add, for example, some flake, like this silver copper flake, these flake are not totally covered by silver, so we have some exposed copper there that can get involved into the click reaction. So if we add a little bit of this, in particular, 25% of the flake, or 20% of the flake plus 5%, for example, of carbon nanotubes, we can do conductive adhesive. Of course, the addition of this is a little bit tricky because we can do it non-covalently. So we can just blend this with the formulation, or we can functionalize the carbon nanotube, for example, and then make it covalently link to the polymer network. This will influence the adhesive strength. But on the other hand, even if we decrease a little bit the strength, we are going to provide a new property, which is conductivity. So we have to balance exactly what we need in terms of the adhesive strength and also on the conductive property. Another interesting thing that we can do with this is that we can also glue metal to glass. As you know, this is challenging because of the difference on the thermal expansion coefficient of the glass and the metal. But basically, we can also use similar monomers to promote the adhesion with between metal and glass surfaces. But what I found even more interesting is that the robust nature of the click reaction allows you to do this reaction underwater. Yeah? So you can coat a surface underwater, you can put the two surfaces together, and then you can promote the click polymerization underwater. And this, for some application, are really interesting. And it does not affect the strength of the adhesive. So this is something that I found also very interesting. And in the last few minutes, I will show you now also another application, which is a more recent application, which is to make anti-corrosion coatings. So, corrosion is a big problem, and among the different metals that undergo corrosion, aluminum is also one of the most problematic metal because of the fast passivation layer that they generate. We use for our study one alloy. This is the AA2024. This is a very important, very resistant alloy that is used when you need a very high ratio of force weight in an application, and this is usually used for high-speed train or for aircraft, and this is basically one of the most important alloy that we have. This alloy contains 92 to 93% of aluminum, and the main component is copper, where we have about 4.4% of this metal. So basically, what is done in industry is that the aluminum is connected to an epoxy top coat, as you can see here, through an inner layer of an organosealant, right, phosphonic sealant. And this is what we do by making a copolymerization with TEOS, this vinyl tetramethyl sealant, and this diamine phosphonic derivative, right? We make a copolymerization, we create this inner layer, and this provides a nice adhesion between the aluminum and the epoxy top coat. So the process to make this coating is pretty easy. Basically, you just take the aluminum, make a solution with all the components, and then you just take the aluminum, dip into the solution for 30 minutes, then you take it out, and then you cure the layer in an oven, right? So experimentally, it's pretty easy to make a large amount of these layers. And here you can see that we get, let me go back. We get a very nice adhesion between the aluminum and the epoxy, which is this one here. So, and we get like a few micrometer thickness of this organosealant layer. What is the problem? That most of this adhesive use aromatic solvent, and there is a lot of effort trying to get rid of this solvent and trying to find alternative that can maybe make it easier or faster or more economic, the connection between these two layers. One of the things we thought is that we can replace or put directly a polytriazole layer between the aluminum and this one, and the organosealant. And this is pretty easy to make it because we take the aluminum, we add a copper 1 salt with a mix of a polyvalent azide and alkyne. So we just select the alkyne and the azide, and then we add the copper 1 ion. And what we are going to make is to create hyperbright polytriazole film on top of the aluminum. Depending on the combination of the monomer that you use, of course, you will get different structure, and this will also influence the strength of the adhesive. So the thickness that we get from these films are between 10 and 30 micrometers. As you can see here, another interesting thing is that you can control the water contact angle, so the wettability of the surface. Okay, so as you can see here, let me just see if I can remove the sound. So in these two videos, you can see that depending on the monomer, you can get a very wet surface or a dry surface. You can see here, this is an aluminum without treatment. This is aluminum with the treatment of one of the alkyne and azide. And you can see that the increase of the water contact angle is quite high. You can see that we make a very hydrophobic surface, and this is pretty good for anti-corrosion, right? So depending on the monomer, you will control this wettability property of the surface. Okay, and here you can see in this slide, you can see that after 60 days, how different looks like an aluminium without treatment and aluminium with the click polytriazole layer on top. And then I don't have time to go into the detail, but we use this electrochemical impedance spectroscopy to investigate the corrosion of these surfaces. Basically, a very high and positive potential of corrosion indicate a penetration of the liquid. What we found was that when we put this polytriazole layer on top of the aluminum, this increase of the potential is not so much, or at least it's not so high, and it does not increase so fast. So we are basically protecting pretty well the surface towards the pitting corrosion. And also the best monomers that we use for the anti-corrosion also provide, as you can see in this plot, the highest strength of the adhesive, right? So we have some monomers or some combination that provide very nice adhesive through a cohesive failure of the adhesive. And if you compare that with the silan and the epoxy layer, they are even stronger stick to the surface. If you think about if these are really well connected to each other, the inner layers, we can take some same image or cryo-same image, and you can see that this is the epoxy coating is not really good in some of the interface, but the polytriazole is actually really good through the interface, right? So and basically I have, I think, 2 more minutes. So this is just to keep on time. This is the summary of what I show you in this talk is basically a very powerful reaction that everybody is now using for many applications. The click reaction catalyzed by copper 1 ion, we can use it or take advantage of this catalysis to make a strong adhesive to metals. Depending on the nature of the metal, we may need to add some copper 1 catalyst, but it is no limit to the metal. We can also make conductive polymer. We can also do adhesive between metal and glass. We can do it underwater. And most interestingly, we can do very nice anti-corrosion coatings for metal like aluminum, right? So this is just one slide that I like to put in this talk, because this Kelly Johnson, a very famous American engineering that was responsible for the design of this black bear. He always say that in material science, simplicity is a key goal in design. So no matter how easy it is, the functionality and the functionality can be very complex, but the way to achieve the material that we want to go to market, for example, has to be easy. And one way to get this easy procedure is to use orthogonal chemistry like the click chemistry. And based on that, we were able also to fabricate, or let's say to design a practical experience that we can just implement in the practical courses in the university. And if you want to read about this, you can have the publication there. Yeah. So as you see, we have a lot of fun playing with this adhesive. And this is pretty much all what I wanted to show you today. I thank you again, the organizing committee, for making the effort to make this nice conference. And I also want to thank, of course, 3 of my mentors that helped me to develop all this chemistry: Professor M.G. Finn, who is now in Georgia Tech, Valerie Focking, Professor, of course, Sharpless. So with this, I think I pretty much use exactly 35 minutes. So I hope we can have some minutes for questions, if any.
Il microfono. Okay.
Now,
Please.
Yes, thank you very much, Professor Díaz David, for your excellent presentation. And I think there is really little to say about water because you were so exhaustive that it's difficult to formulate a question, for instance. At any rate, this presentation, is open for questions from the public. Are there any questions?
Now, I'm watching the chat, and until now, we have not received questions from the attendees, but we are also aware that his presentation is very clear. So possibly we can make questions, Paolo.
Oh, yes. I have one, for instance. Well, I understand that your coatings and adhesive are quite stable to environment. And they are stable also to acids, I understand, or not?
Yes.
Because, for instance, in case of aluminum, it is quite sensitive to hydrochloric acid, usually. But with your coatings, probably it's not.
So that's a very good question. So the way we tested the corrosion was not under so harsh condition, because we use the typical tests are usually do under saline condition, for 60 days, things like that. To be honest, we have not tested under putting, for example, the coating on the hydrochloric acid. So I note that the polytriazole, it depending on the monomer you use as well. Of course, depending on the monomer you use, you may also destroy the coating. But in principle, the hyperbranch polytriazole are pretty stable, so they are really rock. So I would say you can always you can manage to get a very stable. So you just take a click polymer, and just because you put it in acid, it does not really fall apart. So I would say it is possible, but we have not tested.
Sorry, I have just a small second question now, because I know that for some in seawater, for some ships, for instance, one of the problems is to adhesion of organisms, of living organisms from the sea. Is it possible that your coating hampers that?
This is actually an excellent question. This is a project that we are also interested, because, as you say, we have this bioaccumulant on the ship. What we are trying to do is if we can make a coating, but we have to put in this coating, we have to make the monomer need to also be some inhibitor for some enzymes that prevent the stick of the animals. So there's a little bit of biotechnology there, because we need to prove that they are really anti-adhesion. So they inhibit the enzyme that is responsible for the adhesion of this animal. But this is something that is really interesting, and we are looking for to work on this direction.
Thank you so much. And now it is time to pass to the second.
I have a small question.
No, sorry. Elisabetta Ranucci has one more question.
Okay.
Just a small question, because I understand that you have studied many different formulations, either simple, let's say simple polymers and composites. So I think that you can predict, or the correlation between composition, chemical composition, and all kinds of physical properties, mechanical properties, flexibility, etc., chemical stability, durability. So I think that you have a database with many information, with several information. Now, my question is, since this method is so interesting and you have studied so much, what about the future? So what are the future perspectives, the new frontiers of the study? Because I think that it's an unlimited field.
Yeah, it is. I think this is also very interesting as well, because I think I found the challenge of this adhesive not so much on the technical part, but on the society part, let's say. Why? Because we need to convince, or we need to show that not all SIs are explosive compound, right? So there is a conception that the people, as also industry, as soon as they hear SIs, they think about dangerous explosive compound, and therefore anything that contains SI should be avoided. So I think, as you see, we have tested, and you mentioned also, we have tested hundreds of compounds. None of the SI we use are explosive at all. This does not mean that there are no explosive SI, but this is like saying there are no toxic chemical. There are toxic chemical, but we know how to work with them. So SI is the same thing, but we need to really work on making the people aware that some SIs are explosive, of course, but many others are not. And we also have methods to know whether they are explosive or not. And I think this is really what will limit the expansion of this. But in my opinion, like for example, Professor Ferrucci say, this has many applications in many fields. We are looking forward to expand the application, but I think I would like to work on this as well, on this aspect, that making the people not be afraid of using SI if they are not dangerous. Okay.
Okay.
Yeah.
Okay.